Good morning, welcome to the first ABUMPIMP Symposium. My name is Yann Falevoz. I'm in charge of collaboration management and PIM marketing at UPMEM. Today, we are here to delve into the world of UPMEM processing memory technology. Our goal is clear: to showcase the potential of this technology, convince you of its value, and to encourage meaningful exchanges among our speakers and participants. Throughout the day, you will hear speakers who have extensively explored our technology, sharing insights into its impact in various domains. Let's have a look at our agenda. First, we'll start with a keynote session on UPMEM PIM platform, led by myself and my colleague, Julien Legriel, the technical leader on the SDK on application. Next, Juan Gomez-Luna will present latest research using UPMEM technology at ETH Zurich, and research papers will follow, covering various topics such as database management, genomics, AI, and more. Please engage, ask your questions. Let's make the most of this day. Once again, welcome, and thanks for joining. We'll start with the keynote session. Over the next hour, we will begin by providing a comprehensive technology overview, followed by an exploration of the hardware architecture and the intricacies of programming the UPMEM PIM. We'll then navigate through real-world applications we are working on at UPMEM and highlight the collaborative project we are involved in. And finally, we will unveil the evolutions that lie ahead with our hardware roadmap. UPMEM was founded in 2015 by Gilles and Fabrice Lebeau with the aim of providing a solution to the data and energy bottleneck of compute-centric architectures. Indeed, in the case of data-intensive applications, such architecture reaches their limits with communication between the main memory and the CPUs happening through a narrow bus with limited bandwidth, high latency, and most of the energy in the compute node related to DRAM data movement. The solution for this is to integrate powerful compute capacity into the DRAM memory die that is in DRAM. There are several ways to do so. At the beginning in the 90s, processing memory consisted in putting together classical memory with logic in the same chip without changing the memory structure. But technology evolved, and the logic progressively integrated the memory structure either in its periphery or in the memory array. It was then necessary to introduce new terms to distinguish the technologies. Thus, one referred to near-memory computing and in-memory computing. The UPMEM technology falls in the first category and is the first PIM architecture to be commercialized in real hardware. For now, processing in-memory computing only exists in the form of research project. There is no product available on the market. We sold our first server in 2020, and since then, we have proven the capacity of the technology to speed up and reduce the cost and energy of a large number of applications compared to CPU, GPU, and FPGA. But let me explain the technology in more details. An UPMEM PIM server is a standard Xeon x86 application server where most of the DIMM slots have been populated with PIM DIMMs. Standard and PIM DIMMs coexist in the server, and the firmware is made aware of the specific configuration. The typical configuration totalizes 20 PIM modules. A module takes the form of the standard DDR4 2400 DIMM. It has a capacity of 8 GB and totalizes 16 PIM chips. Chips are produced using DRAM processes without manufacturing implication. Inside each chip, 8 processors coexist, and we call that processors GPU, standing for data processing unit. You probably done the math. A typical configuration totalizes 2,560 GPUs for 160 GB of PIM DRAM. A DPU is a simple modern general purpose processor which shares the access with the host through a DRAM RAM called main RAM. Instruction and data caches have been replaced by instruction RAM and working RAM. DPUs are independent from each other's memory and they run asynchronously. Inside each DPU, 24 threads can execute independently, and each inter-DPU communication takes place through the host CPU. This architecture allows each DPU to work efficiently on its own fragment of the dataset, and even with its own programming routine if chosen to be different. The technology comes with a set of tools that make the porting of applications as smooth as possible. Each DPU can be programmed in a familiar language with standard tools and skills. UPMEM provides a complete software stack that enables DPU to be programmed in C and APIs in common languages for host programming. Communication libraries make it easy to configure the DPU, organize the distribution of data, scheduling, and retrieve results. The compiler for the DPU target is based on LLVM and comes with some tools from the LLVM compilation toolchain. I'm now passing the floor to Julien to go deeper into the architecture, the programming, and the applications.
Okay, so hello everyone. Yann has already introduced you what is processing in memory and what is the product that we developed at UPMEM. Now I will try to give you a little bit more details about the architecture and specifically try to highlight some of the specificities that impact how it's programmed. Okay, so we have seen that the UPMEM product is actually a DIMM that you can find in the server. This DIMM has some different chips, and each chip has 8 memory banks of 64 megabytes. Those memory banks are connected through a different interface to the CPU. So that's a normal memory chip. And what we do at UPMEM is to add those elements in yellow. So one processing unit per bank, which we call DPU for data processing unit, and a control interface. So each DPU has very fast access to its own memory bank, but it cannot communicate directly with other DPUs. They are controlled by the host through this control interface that is memory mapped in the DPU address space. So for the CPU to send command to those DPUs, it's just about writing at the right memory address. And typical command would be to boot the DPU, to check the status of the DPU, is it running, is it in fault, if it's in fault, what is the fault, this kind of things. Okay. So previously we have seen the view of a DRAM chip. Here we are zooming to the view of one memory bank. So on this picture, important to say is that for ease of understanding, we have represented the DPU as a very large element that in practice the memory array is taking the largest fraction of the area. So what is inside this DPU? First, we have a pipeline to execute instructions. On the next slide, I will talk a little bit more about the pipeline. But there are several hardware threads that are running and sharing this pipeline. All these hardware threads have their own set of registers. They have their own program counter, but they share the same instruction run. So this means that in your program, you can do, for example, something that based on the thread ID, you want some thread to do something and some other thread to do some other thing, but they still execute the same program. Now, the instruction run is 4K, can contain 4K instructions, so as an absolute number, it doesn't say much, but I hope you will see when we talk a bit about the application that in practice, it's enough to contain quite complex programs already. In terms of memory, there is a 64 kilobytes scratch pad memory, which we call W1 or working map. That is a memory that is directly accessible by the pipeline through the instructions. And then the memory array that we call main1, so M1, is accessible through a DIMM engine that can be programmed by the hardware threads in order to issue a transfer from the main1 to the scratch pad memory. An important thing to note on this slide is the presence of a NUT here that implies exclusive ownership of the memory bank by either the CPU through the DPI interface or by the DPUs with DMA. So on the software side, this implies that we cannot parallelize the execution on the DPU and the communication to the memory. And the roots of this is actually a hardware constraint. So this is linked to the DPI protocol. It will be too complex to have in parallel the DPU and the host access the memory array and still respect some timing that the DPI protocol expects when the CPU accesses the memory. Okay, and this mix is controlled by the control interface as well, so the CPU can send a command. For example, when we want to boot the DPU, there will first be a command to switch the mix and give the access to the bank, to the DPU. On the other end, if we want to do the transfer of data, the host will set the mux to the CPU side to be able to transfer data. Okay, so about the pipeline is 11 stages, so it has 11 cycles. As I said, there are different hardware threads that are interleaved in their execution. In the current architecture, it's up to 24 hardware threads. And when an hardware thread puts an instruction into the pipeline, it takes 11 cycles to go out, and only then can the same hardware thread put another instruction in the pipeline. So that at any point in time, there are no two instructions from the same hardware thread in the pipeline. And this simple design is good to have a simple processor in a DRAM process. It's much simpler than a complex CPU where you can have out-of-order execution or branch prediction and things like that. But on the software side, it has a constraint. It is that we must expose more parallelism, because for this pipeline to be fully used, we need at least 11 hardware threads that are running in parallel. And in practice, we often use more because the hardware threads do not have, at any point in time, always an instruction to be ready to be put in the pipeline. They can be waiting, for example, on synchronization, the barrier or whatever, or they can be also waiting for a DMA transfer. Okay, let's take a step back and look at the system overview now and about what would be the typical workflow of an application in this system. So in our server, we have CPUs first, so usually we have two sockets with two CPUs. We have standard or legacy DRAM, and we have the UPMEM PIM modules. So typically you have an application that is running on the CPU, it's using the standard DRAM modules for its memory. And at some point, there is some computation you would like to offload to the PIM. So it's working as an accelerator model. We have to first initialize those DPUs, those processing units. So initialize means using the APIs of our SDK to allocate the DPUs, to load the program inside those DPUs, to copy maybe some data and so on. And then usually we enter in the loop where we first copy some data, copy some inputs, launch the execution, gather the results from all the DPU, maybe do some kind of reduction on the CPU side, and do this loop again. And as said before, there is no parallelism between those things, copying and execution. However, we can still have some asynchronous behavior here where we do not wait for the code that happens on the execution, and we can execute something in parallel on the CPU, for example. One last point to discuss about the specificities of this architecture is relating to the communication between the CPU and the DPU. So normally when the CPU is writing 64 bits value to the memory, what happens is that you have each of the bytes that is going to a different memory chip, and actually to the same memory array of different chip. So this is good in terms of latency of the memory access, but when you are doing PIM, that is not what we want, because usually you have a continuous buffer of data on the standard memory for the CPU, and you want this continuous buffer to go inside one DPU entirely. So what happens is that OSDK takes care of this problem. We provide a buffer for each DPU, and OSDK does the transposition to make sure that the contiguous buffer of data reaches each DPU. but still it puts some additional constraint that's okay. So when we do that, this transposition is light enough to sustain the full bandwidth of the DDR bus, so we can reach the full bandwidth when we are doing this transfer. But it still poses a constraint that we have to communicate with many GPUs at the same time. So in this example, if I wanted to transfer only to this GPU at one point, I will transfer one byte here, but all this other will be garbage. So we're just using 1/8 of the total bandwidth, and that will not be efficient. So that's something to take into account for the performance, and our API is also encourage the programmer to perform the transfer for many GPUs in parallel. Okay. So that's ended the part on the high-level architecture. Now let's start to talk a bit more about how to program this architecture. And let's start with the SDK and application design flow. So when designing such an application, we have two programs. There is a CPU program. So this one will be compiled with the x86 toolchain. We support only x86 architecture as of now, Intel server. You will use the SDK host library to perform the GPU management, like allocate GPU, copy data, or asynchronous orchestration and so on. And these SDK libraries are actually available for different languages, for C, C++, Java, and Python. On the GPU side, so we have a program that will be written in C, with a subset of the libc available. Not everything is there. We don't have the map library support. We don't have input-output, for example. But if you're interested, the whole list of what is supported is present on our SDK documentation on our website. Usually, we have one common DQ program for all DQs, but it's not mandatory. We could load, if we want to, different program in each of the DQ. This program is compiled with the compiler DQ CN provided by UPMEM, and which is based on Legriel 12. This program will use DQ libraries in order to manage things like NRAM WRAM transfers or synchronization primitives, barriers, semaphores, and so on. Or, for example, also to check the performance by setting the performance counter to count instructions of cycle on the DQ side. Additionally, there is a number of profiling and debugging tools. For the DQ, we have an extension of LLDB, DQ LLDB, that has additional commands, for example, to attach to a DPU, to examine the memory, to do a core process. On the host side, we have a profiling tool which is based on UXPerf. It can also output quite a nice chart of the execution in order to understand what's happening in terms of orchestration and identify potential bottleneck into that. So on the system side, I will not develop this part, but just to say that in order to work, our system needs a specific driver that we also provide. And we also have actually to modify the BIOS, so to provide a modified version of the BIOS. And that's kind of a painful dependency that we want to cut. But as of now, we still need to do this BIOS modification in order for the PIM memory to be recognized by the system. Then in terms of targets, so we have a software simulator. So this one, if you download the SDK and you start developing a small program and running it on the CPU, the default target will be this one. So it's a software simulator. It can contain maximum 64 GPU and it's purely functional. And then if you run your program on the real hardware, then it will target the real hardware. Okay. Let's talk a bit about the instruction set architecture. So the DPU has a proprietary with triadic instruction set. It has common operators, like for arithmetic, load, stores, shift, rotate, multiplication, division, and also specific instructions for DMA access. Now there are bits of important points. One is there is no floating point unit in the DPU. every floating point computation is made using a software library, and that's a bit costly. For example, a 32 float multiplication is around 200 cycles. So what this means is, for all that concerns floating point, quantization is really the way to go. There are also no vectorized instructions, with the exception of one which is called CMPP4, and that's a comparison of different bytes in parallel, which means that the parallelism has to happen at the hardware thread level. In terms of integer arithmetic, there is a 8x8 multiplication instructions. For larger integer representation, it will take more time. For example, for 32x32 multiplication, it's based on multi-step instructions, which can take up to 32 instructions. On average, much less. That's the worst case. But just to point out that the biggest the integer representation, the less the performance will be. Now, this is more about the limitation. One of the strengths is a rich set of conditions for jumping on the arithmetic instructions, and I will try to give some examples on the next slide. And finally, one thing I wanted to mention is, from our experience, it can be rewarding to sometimes spend time to analyze the hotspots at the assembly level, even if it doesn't mean really coding in assembly, but just looking at your assembly code in order to identify the bottlenecks and possibly redo your code from the C level. Okay. So these are two examples to give you a feel about what I meant by which set of conditions in the instruction set. So the first one is a 16 by 16 bit multiplication. And as I mentioned before, this is not natively supported. So we have to do 4 8x8 multiplications and combine the results. That's what this code does. But what is more important is the instruction there. So this one is the first one. It's actually multiplying the two 8 bits, this significant 8 bits of the inputs. And it has a condition here which is called small, that is doing one thing is to check the inputs. And it is true when both of the inputs are actually represented on less than 8 bits. So when this condition is true, then it can directly jump to the exit, and all this code will just be one instruction. So what this means is, if you have a program where you have to use 16-bit arithmetic because you think, okay, this is what I need, but maybe in many cases your value is actually represented on 8 bits, then this code, this multiplication will actually just take this one instruction thanks to this condition. Another example is the case of a reverse loop. So here, this add instruction is actually implementing the loop. It's decrementing the R1 register, which contains the I value. And it's also having a condition here on the results. So here it was a condition on the inputs, here it's a condition on the results. When the result is non-zero, it loops back to the beginning of the loop. Okay, so that's just a few examples to give you a feel. If you want to know more about this instruction set architecture, everything is detailed on our website on the sdk.upmem.com, so you can have a look in order to see more topics. Okay, so I wanted also to be more concrete, to give you a feel of what the code looks like. It's a very basic, you could say, do-me example that has nothing interesting, but just to give you an idea about what DPU code would look like. So here, this code, what it does is simply has 10 values, 10 integer value in the main RAM, loading this value into the scratchpad memory, adding them up, and writing the results into the MRAM. So what we can see, first, it's a C program. There is an include here from the DPU libraries that give access to NRAM read and NRAM write, for example, that are used to issue a DNA transfer and transfer some data to and from the scratchpad memory. We have this MRAM keyword here that is used to specify that a given variable should be put in the M1 section of the binary, and that will be loaded in the M1 of the DPU. We have other keywords, for example, like DMA line, so that is used to tell the compiler that this variable should be aligned on 8 bytes because it will be used in the DMA transfer, and DMA transfer has specific element constraints. So that's a kind of different thing we can see in this program. So now let's have a look at the host code, what it would look like. This is an example in C. As I mentioned, we have support for other languages. Here what we see. So first, here we have an include for the C host library header. That gives access to different functions like DPU alloc to allocate to DPU. So here I'm allocating only one DPU inside this DPU set. There is a load function to load the program. We pass to this load function the string with the name of the binary of the DPU that we have compiled with DPU clang. Then we can use, for example, this DPU for each macro to loop over the DPU set. In this case, we only have one DPU, so it will actually be one loop only. And we can copy data. So here to copy data, again, I'm specifying a string with the name of the variable on the DPU side to which I want to copy. And how does the host know the address of this variable? Is because it's happening in the load. So when we load the program, the host will store the address of specific variable that he wants to be visible from this program. Then we have the launch function, the DPU launch function, to launch the program to boot the DPUs. So here what it does is not only to launch the program, but also to wait for the finish of the execution. That's because we have used the synchronous mode. So under the hood, what the SDK will do is it has some polling thread, and those threads will regularly check if all the DPUs are finished and return to this execution when all the DPUs have finished their execution. We have also asynchronous mode that is more complex. So for example, that enables to this call to return immediately, do something else on the CPU. That also enables actually to have asynchronicity between execution on different ranks of DPU, rank being 64 DPU, and that can be good for load balancing. So that's there are more complex cases of execution. It's out of the scope of this talk today. But there are additional resources if you want to know more. First, there is our SDK website with all the documentation. And we have also the training that we do usually for people who want to start programming on architecture that lasts about 1 hour, 30 minutes. And that is also available in video on our website and on YouTube. And this training, we show a complete example of a checksum. What are the possible pitfalls of programming on the DPU, how to use some profiling tools, and so on. Okay, so I have shown a very basic example to give you a feel about what it would look like. But now I want to talk a bit about the meaningful applications. And that's a pretty broad topic. UPMEM has invested early into developing applications, and we have also partners with partnership with a lot of research labs, research teams that are doing a great job of developing new applications and benchmarking algorithms. So you will see a lot of the examples during the day with some presentations. Here I just want to give you a quick overview of the main application domains that we have targeted at UPMEM, and some of example of application where we can reach good speed up. And first, I want to start with a question which is, which one could ask is, which is, what kind of applications are suitable to be run on this processing memory architecture? And also, again, I think it's a very complex question. There can be a lot of discussion on that. I also don't believe there is one recipe to tell if one application is a fit and how we could implement that. But based on my experience, I can try to give a few more or less obvious things about what makes a good application. And first of all, I think it has most of the applications that work well are largely data parallel, because there are a lot of GPUs in the server, more than 2,500. Each GPU has also hardware threads that run in parallel, and synchronizations are non-negligible cost, right? Because, as mentioned before, the GPUs cannot communicate between each other. You have to go back to the host, and even to the host standard memory in order to perform this computation. So obviously on the thread level, it's totally possible to do task parallelism, but that's also a bit more complex. Then there are also other problematics that are classical in parallelization, like, for instance, having a good load balancing, and that can be complex, especially if your execution time depends on the data and not only the data size or something. So usually we resolve this problem by doing batching. We send multiple queries to the system at once, with the hope that the execution time will average out and get a better load balancing. And this has one consequence is that I think the PIM architecture shines more when you have when you are targeting throughput rather than latency because of this batching. Then obviously we are talking about processing in memory, so the strength is a massive memory bandwidth and applications that are memory bound on the CPU or that have a low operational intensity, meaning they have to load a lot of data in the cache for just few operations, are good candidates to be ported on this architecture. One case that works really well, we see in the example, is a case where we have a large static databases in the PIM, and we have to send a few requests of data, because obviously that's a case where the trade-off between computation, the ratio between computation and communication is good. Yeah, and finally, one thing I wanted to mention is one also should sometimes consider redesigning algorithm in order to get good performance, because that's a new paradigm, and maybe some CPU implementation have been tailored to with a memory hierarchy of the CPU in mind, and that may not be suitable for this application. Now, in terms of goal, I think mentioning the PIM application is kind of key for PIM product adoption. Surprisingly, we see that customers or potential customers don't want to develop applications by themselves. They don't want just the hardware, they want the hardware and not just shape applications to use. So we are trying to move from just doing algorithm benchmarking to also invest porting some standard libraries on PIM. And that's obviously a much larger work, which is with our limited resources quite ambitious, but we are trying to slowly go in this direction. And finally, I think the application is tightly coupled with the SDK enhancement. So when we develop application, we also try to enhance the SDK and get better performance for SDK. Okay, so let me start with one domain of application, which is analytics, and an application that we developed quite some time ago, which is index search. So an index search engine is an engine that looks for items in the database based on a keyword from the user. So for instance, if it is about text search, you have a large corpus of text documents, say the Wikipedia dataset, and you want to search all the documents that match a specific term, or maybe that match a specific phrase, or a prefix, things like that. And the data structure used for this kind of problem is called an inverted index, and that's similar in concept to the index at the end of the book. So you have a list of words, and for each word, you have a set of documents that contain it, and maybe some additional information like frequency of the word in the document, or position of the word in the document. So for the case of the GPU, that's typically a case where you have a large kind of database that you can put in the PIM, this inverted index. We can easily parallelize it because we can create segments with subset of documents, and each GPU will have its own segment, and each GPU will do a search in parallel and will aggregate the results on the host to get the final results for the query. So that's kind of a good example. We also do batching in this case in order to have better load balancing, as I mentioned before. And for prototype that we did, which is called UPMEM Index Search, for that, which is more than 600 queries per second on throughput for exact phrase match on the Wikipedia dataset. And that's kind of promising when we look at the standard library for search, which is what we use in the industry, which is Apache PIM, that reports 30 queries per second in the nightly benchmark on 64 core CPU. So obviously this is not a fair comparison. On one hand it's a prototype, on the other hand it's a full-flavored search library. But now we are trying to actually we have a project called PIM where we are trying to work directly on this thing and create an extension of that library to be able to port some of the queries to PIM. And we hope that for the first query we get also good results to start with. Okay, another example in analytics is the hash join. So that's a kernel in the database. We have worked on this with a partnership with the team at Intel that came to us and say that this hash join is actually a bottleneck in the whole database management system, and they wanted to see if PIM can accelerate that. So we actually worked on that. Initially you have really big tables that you need to send to the DPU. This table needs to be partitioned between the DPU if you want to do it in a data parallel fashion. And this partition has to be quite smart because you want on each DPU to have the same subset of keys from the different tables so that you'll be able to do the job in parallel way. So we have a first partition phase, hash partitioning, that happens on the DPU, and then we transfer those partitions to the DPU to do the actual job. When we were doing so, we actually identified a pretty important bottleneck in this communication between the partitioning and the join step, which requires an enhancement in our SDK, which we call scatter gather transfer. So that's the idea to have a transfer that can directly take pieces of data from the DPU and gather them in the same area on the host. So that involves some low-level changes in our SDK, and that really was the key to unlock the performance there, because otherwise we were suffering too much from data reorganization on the host side and mem copy and so on. And in the end, we see that we can reach around 9x acceleration versus data fusion, which is a standard framework on the CPU, and we actually tried different framework, and this one was giving the best results on the CPU. And I want to say that this 9x is also including the time to transfer those big tables to and from the DPUs. And that's interesting because in this case, we are not talking about small communication, it's quite already a big transfer, and still we are able to get good acceleration. So these results make us think whether we should look at porting another database management system, for example, like the DB on the DPU. So we are considering this possibility right now. Okay, so another domain is machine learning. In UPMEM, we have worked mainly on two different workloads, which are decision trees and k-means, with pretty decent results on k-mean, and I think very good results on the decision trees. So this work is also a part of a larger work that we did with ETH, Zurich, so where they also worked on other workflows like linear regression and logistic regression. And that work has been published in 2023. And there will be a presentation in the afternoon into detail of this work, so I will not go into detail. Just to say that this is an example that even for applications that are typically tackled with floating points, when we perform quantization or when we use other strategy, we can still get good results with this architecture. And last but not least, an important domain of application is genomics. UPMEM has a long-term partnership with Elisa and Yann to work on genomics. So we have done different applications there, mostly related to sequence alignment. So sequence alignment is core process that you have, post-process that you have to do when you sequence the genome, and you get this particular file, which is actually a list of small pieces of the genome. And that's also a case where you have this large database that stays in PIM, because you have to align these pieces against a reference genome that is a large static database that can stay in the PIM. So we have worked on short read alignment and variant calling. We have worked on long read alignment, and there will be a presentation by an Mondial PhD between Adnan and Mirza in the afternoon of this work. And we also have invested a bit of time to see if we could work directly on standard tools in this domain, like BWA, Burroughs-Wheeler aligner. Unfortunately, we show that Burroughs-Wheeler aligner is clearly a memory-bound workload, but we have seen that it's very difficult to parallelize. It's actually a quite complex algorithm. It's interesting to look at it if you don't know that algorithm. And we also did a work on PIM, which is the main contributor to variant calling in GATK pipeline in terms of execution time. And that is a work that was done initially by Techion and also with Adnan and ETH.
As we conclude our exploration of PIM application, it's important to highlight the implication of UPMEM in a number of collaborative research projects supported by either the European Commission or the French government. In particular, UPMEM has been distinguished as a beneficiary of the highly selective EIC Accelerator program. Among its array of projects, I'd like to present three that illustrates the various impacts of our efforts. The BioPIM project is about co-designing algorithms and data structures commonly used in bioinformatics together with several types of PIM architectures to obtain the highest benefits in cost, energy, and time saving. Several today's speakers are involved in the €3 million project. The Sustainable project is about developing a sustainable and interactive machine learning framework that will comprehensively prioritize and advocate energy efficiency across the entire life cycle of an application and avoid AI wastes. This project received a grant of €4.3 million from the European Commission. Stratum aims to develop a 3D decision support tool for brain surgery guidance and diagnostics based on multimodal data processing through AI algorithms that will be integrated as an energy-efficient content care computing tool. This project received €10 million in funding from the European Commission. This project highlights a strong network of academic and industrial partners, as well as a diversity of fields in which our technology finds purposeful application. As you have a good understanding of the hardware and the intricacies of the programming, as well as an overview of the applications, let's look at our exciting plans for the future with our hardware roadmap. Our next generation models are just on the horizon, with silicon bring-up completed and system bring-up in progress. There's new models offers an increased operating frequency or up to 40% lower power consumption at same frequency. They allow the host to access to the working RAM while the DPU on the bank, opening the way to producer-consumer pattern and optimize data flow. They benefit from new hardware maintaining feature, bringing new insights into the system behavior. And they offer DPU switch-off capability, slashing the idle consumption by 90%. As we anticipate the arrival of this next generation, we are already hard at work on the following one. Our under development PIM-derived models promise even greater potential with an enhanced control interface that is 10 times more efficient. The concurrent access to the working RAM will be replaced by concurrent access to the main RAM, offering much larger features for the user consumer pattern. It will be the opportunity to integrate new operators informed by our involvement in collaborative projects, which allow us to identify the most compelling options. It will offer an improved system integration, minimizing the need for BIOS modifications. We are also starting to work on a roadmap for a dedicated chip for AI applications, such as LLM. In our quest for seamless integration, we explored the world of CXL, which led us to an insightful proof of concept. This approach simplifies the system integration, avoiding the need for BIOS modifications, but at the cost of a higher price and power consumption. Exciting horizon awaits as we're starting a new initiative with a major player in network devices to build a system on chip with the same functionalities. UPMEM server's journey accelerates through the partnership with the major server manufacturer, transitioning from Skylake to Ice Lake. This evolution brings with it a move to production servers, an increased number of memory slots and channels, and an increased PIM and legacy memory density. The servers are planned to be released in the coming months, and we are at an early exploration stage regarding Sapphire Rapids. Our commitment to progress extends to open firmware implementation through a partnership with another major server manufacturer. This collaboration is driving our early exploration through the common goal of developing a proof of concept. As we delve into our cloud infrastructure, let's start with some key figures. It hosts 10 servers, engages 56 teams for a total of 2,012 active users, and we reached almost 31,000 hours booked to date. The above-mentioned breakthrough will find their first home in this cloud, but we are not stopping there. Our focus extends to storage with the integration of local disk to the servers and seamless preloading of datasets to SFTP. As we come to the end of this keynote, we have been able to explore the UPMEM PIM architecture, to delve into its hardware architecture, to understand its programming interfaces, to witness its application in various domains, and to foresee the plan for the future for the hardware roadmap. There's insight underscore the transformative power of PIM, and we invite you to reflect on its potential for your own work and industry. The floor is now open to your questions, and we're looking forward to excellent thought. Thank you for attending.